In this video, we're going to look at a question which is mainly to do with moments, but actually involves a few other areas of physics as well. Now, if you can't read the writing here, don't worry, because the values you need are clearly written in each of the questions. So pause the video now and try all parts of this question. Part A. The ball is made of a metal of density this, diameter this, calculate the weight of the ball. So to calculate the weight, we obviously need the mass. So we need to write down that density is mass over volume, rearrange for mass. So mass is density times volume, which is 7,050 kilograms per meter cubed times by the volume. Volume of a sphere, because it's a ball, is 4/3 pi r cubed. And this is the diameter, so we need the radius in meters, which is 0.045 divided by 2, which is 0.0225 meters. So this is going to be 7050 times 4/3 pi times by 0.0225 cubed. Which is 0.336 kilograms. So the weight is 0.336 times by 9.8, which is 3.3 newtons. Right, rounding that up to two significant figures, because that's what we've been given in the question. Part B, the distance from the surface of the ball to the pivot is 16 centimeters, so this distance here. As shown in the diagram, calculate the moment of the weight of the ball about the pivot when the rod is horizontal, given appropriate unit. So when it's horizontal, what is the moment of the weight of the ball? So we need to use the idea that moment is force times perpendicular distance. What is the force? Well, we've been given the weight of, well, we've worked out the weight of the ball, so 3.3 newtons. Times by the distance. So what is the distance? Well, it's 16 centimeters, which is 0.16 meters. But that's not where the weight is acting. The weight is acting from the center of the ball. So we need, again, the radius, which is 0.0225 meters. Which is 0.012 Newton meters. So I've converted it all to meters. It's obviously this is the unit. If you hadn't actually converted this to meters and you kept it all as centimeters, then you could have written Newton centimeters, but it always usually makes sense to work in meters. Part C, the spring is attached at 12 centimeters, so this distance here from the pivot, and we know what the spring constant, so the stiffness just means spring constant. And if you're not sure exactly what that means, just look at the units, and that is obviously the unit of spring constant. So calculate the extension of the spring when the rod is horizontal and the spring is vertical. Assume the mass of the pen and the mass of the rod are negligible. So there's two steps to this. We need to work out the force that the spring is exerting upwards, and therefore the force that is on the spring, and then we can work out the extension. So the first thing we need to do is use moments. So the anti-clockwise moments are going to equal the clockwise moments. So the anti-clockwise moments we've already worked out from part B. So actually we don't need to write out this calculation again. We can just say it's 0.012 Newton meters, and that's going to be equal to the force from the spring times by its distance, which is 0.12 meters. So the force is 0.1 newtons. Probably didn't even need to type that into my calculator. In fact, I actually made a mistake the first time I typed it in. So sometimes it's actually easier to just do it in your head. So the force is 0.1 newtons. We want the extension, so we need to use this relationship here, and the extension is the force over the spring constant, which is 0.1 newtons over 80 newtons per meter, which gives us an extension of 1.25 times 10 to the minus 3 meters. Finally, part D. Before an earthquake occurs, the line being drawn on the graph is horizontal. Explain what happens to the line on the graph paper when an earthquake is detected and the frame of the seismometer accelerates rapidly downwards. So the frame moves downwards. Which way is the line going to go? You might instinctively think the line goes down, but that is not the case. So why is that? So the frame moves down. Now the ball is heavy, okay, and it tells us that. So that means it's very massive, has a lot of mass, which means that it has inertia, which is resistance to movement. So inertia keeps it in place, only for a short period of time. But it does nevertheless mean there is a delay. So what does that mean? The frame has moved down, the ball has stayed roughly in place, so the line is going to go up. The line on the graph will move up, okay? And then after a period of time, what will happen? Either the frame will move back up again, in which case the line moves down, or if you just imagine the whole frame moved down and stayed down, then after a period of time, obviously this ball is then going to drop, right? Because the arm will be up like this, and obviously that's no longer in equilibrium, so it will then move down. So after a period of time, the ball will fall, and the line will be drawn downwards. But I think actually really all they want is this first part here.